subject Computer Organization and Architecture. In this subject we have started Unit 2, that is Basic Computer Organization and Design. In this unit we are going to see today the topic that is Computer Instruction. So let me start with the topic that is Computer Instruction. There is total 3 instruction formats are available for our basic computer device that we are going to design. These 3 formats are memory reference instruction, register reference instruction and IO instruction, or you can say IO reference instruction. For this instruction we have decided that our instruction will be of 16 bit, and from this 16 bit 12 bits from the LSB side will represent your address or some register operation, and remaining 4 bits will represent your operation code. Okay. From this operation code, we have also divided that your 12, 13 and 14 number bits will represent your opcode, and your 15th number bit will represent whether you have used direct addressing mode or indirect addressing mode for your memory reference instruction. Okay, for rest of the types like register reference instruction or IO reference instruction, this 4 bits will represent your operation code. Okay, but for your register memory reference instruction, this 3 bits 12, 13 and 14 bits will represent your operation code, and 15th bit will represent your ith bit, that is your whether you have used direct addressing or indirect addressing. Okay, so if we consider the memory reference instruction, then for memory reference instruction you have operation code 000 to 110. That is your total 7 operation code, that is 000, then 001, then 010 and so on up to 110. Okay, so you have total 7 memory reference instruction. In memory reference instruction you will perform some task like addition or doing ANDing operation and so on with the content of some memory location, and that memory location will be provided by this address line. Okay, or you can say by this address given by this address field. And similarly we can use these register reference or IO reference instruction in which you are directly performing operation on some content of register, or generally it will be accumulator register. Okay, for example clear the content of accumulator, complement the content of accumulator and so on. For this your operation code will be fixed, that is 0111, and for IO reference instruction your operation code will be like 1111. Okay, so this is the fixed thing that you are going to be using for our basic computer system that has a total 3 instruction format. Each instruction is of having 16 bit, and from this 16 bit 4 bits represents your operation and remaining 12 bits represents your address field or operation. Okay, so this is our basic instruction format, and in this memory reference instruction, as we know, if your ith bit is a 0, that means you have used direct addressing mode, and in this case this address field represent your actual address from where you have to access your operand and perform the operation that is given by this opcode. And if your ith bit is 1, that means you have used the indirect addressing. So this field where here you have stored the address is not your actual address, but it is your indirect address. So first you have to find out this address, then go to that address and find out actual address where your operand is stored, and then access your operand from that location onwards. Okay, so this is the basic structure having 16 bit instruction, 4 bits for opcode and 12 bits for address. So next let me see how you can represent your memory reference instruction. So this is the list of the memory reference instruction. As we have discussed earlier that we have total operation code for the memory reference instruction is from 000 to 110. That means we have total 7 operation code for this memory reference instruction. That means we can use total 7 instruction for as a memory reference instruction. In this, ith bit will represent your direct addressing or indirect addressing. If your ith bit is 0, that means you have used direct addressing method, and if your ith bit is 1, then you have used the indirect addressing method. operation will be same, that is ending or adding or loading. That operation will be same, but how you will access your data will differ by this ith bit. Okay, so now let me see one by one this instruction. First instruction is the AND instruction. In this instruction, you will do the ANDing operation of some memory content that you have provided in the address field and the content of the accumulator. Okay, so and the result of this operation is going to be stored in the accumulator. So this is the basically instruction for the ANDing operation. Then you can use this add instruction. This instruction is used for adding some content into accumulator, and that content is of some memory location that you have provided in this address field. In LJIET instruction, you will use the you will load the content into accumulator of some memory location. In ST instruction, you will store the content of accumulator to some memory location that is you have provided in this instruction by this XXX. Okay, in BUN instruction, you will do the branch unconditionally, that is used for changing the sequence of your program. Okay, if you have used instruction like BUN 500, that means you have to now start your instruction execution from the address that is provided in this instruction, and that address is over here is 500 because you have used the instruction BUN 500. So now onwards your instruction is executed from the location 500. Next, you can use this BSA instruction, that is branch and save address. In BUN instruction, you are doing unconditional branching, and in BSA instruction, you are doing the branching but with saving the return address, so that whenever your instructions execution or your sequence or your subroutine is executed, you can return to your main program. Okay, then you can use this ISZ instruction, that is increment and skip if 0. This instruction is basically used for the counter generation. Okay, in this instruction you are going to store some negative number at some memory location that you have provided in this instruction. For example, ISZ 200. That means you have stored some number at location 200, and then you will increment that number, and you will increment up to that time where up to when its content is not 0. And after incrementing, you will check whether your condition is fulfilled or not, that is your content is 0 or not. Okay, so by this way you can use this ISZ instruction. This we will see with example further in detail. Here we are going to see how the operation code for this instructions are generated. For example, if we consider this AND instruction, then it has an opcode of 0XXX or 8XXX. That will depend upon your addressing mode, whether you have used direct addressing or indirect addressing. If it is direct addressing, then your hex code will be 0 and then your address that you have used in your instruction. And if you have used indirect addressing, then 8 and then your address. Let me see with the example. For example, if we consider that we have instruction like this, that we have used this AND instruction, and it has a operation code, or you can say address field of 205. Okay, so this for AND instruction, and if we consider that this our instruction is of direct addressing mode, so for direct addressing mode your ith bit will be 0. Okay, so ith bit will be 0, and rest of the 3 bits for AND operation it should be 0 0 0. Your operation code of 3 bit is of 0 0 0. So we will use here as a 0 0 0, and then we have to use this address field, that is 205. So we have to write here 2, then 0 and then 5. This 205 is in a hex number, so we have to represent it in a binary term as a 0010 for 2, then 0000 for 0 and 0101 for 5. So by this way we have this operation code as a 8 or 0, then 2, 0 and 5. If you have used direct addressing, then your operation code will be like 0, 2, 0, 5. And if you use indirect addressing, then your operation code will be 8, 2, 0, 5. So by this way you can design operation code for any of instruction that will be like 0 or 8. That will be like for add instruction it will be like 1 or 9. For LE instruction it will be like 2 or 8 and so on. But the rest of the 12 bit will depends upon your address field, from which location you have to access your opera. Okay, so from for this instruction your 205 locations, memory content of your 205 locations is ended with the accumulator and result is stored into accumulator. Okay, so by this way you can use any of your memory reference instruction. Next we will see the resistor reference instruction. In the resistor reference instruction, you are performing some operation on the content of accumulator. Okay, so let me see a resistor reference instruction one by one. First one is a CLA, that is instruction for clear accumulator. In this instruction, your content of your accumulator is going to be clear. Okay, and this term represents its hex code. How these hex codes are generated, then that we will see further. Next instruction is a CLE. This instruction is used for clearing the content of E flag. Okay, then you can use CMA instruction to complement the content of accumulator. Then you can use the complement E, CME instruction to complement the content of E flag. Okay, then to circular or circularly shift the content of accumulator through E flag, you can use CIR for circular right shifting and CIL for circular left shifting. Then you can use INC instruction to increment the content of accumulator by 1. Then you can use this SPA, SNA, SZA or SZE instruction. These are for skip instruction. For SPA instruction, you will skip the next instruction if the accumulator's content is positive. How you can find out this accumulator's content is positive or negative? You have to check the MSC bit. Okay, if MSC bit is 1, then your content is negative. If your MSC bit is 0, then your content is positive. Okay, so for this SPA instruction, the content of accumulator is going to be checked, and if this content is a positive, that means it has a 15th bit as a 0, then your next instruction is going to be skipped. And generally in this skipping, you are going to using some branching instruction. Okay, and then you can use the SNA. In this instruction, next instruction is going to be skipped if accumulator's content is negative. Okay, then next instruction is SZA. In this instruction, your next instruction is going to be skipped if your accumulator's content is 0. And next instruction is SZE. In this instruction, you are going to check the E flag. If the E flag is 0, then your next instruction is going to be skipped. And last one for this resistor reference instruction is hold, HLT instruction, to hold your computer. To tell the assembler that your instructions are ended over here. How this hex code are generated, let me see with one example. If we consider the instruction that is CLA. In this instruction, as we know that for your all of your resistor reference instruction, the first 4 bit of your instruction operation will be 0, 1, 1, 1. This will be fixed for all of your resistor reference instruction. That means your 4-bit pattern for first 4 bit will be 7. For next of the 12 bit, we have total 12 instruction, and this for each one of instruction, any of 1 bit will be 1 and all rest of bit will be 0. So for this instruction, if we consider the CLA instruction, for this instruction your 11th bit is 1 and rest of the all bits are 0. For CLE instruction, your 10th bit is 1 and all of the other bits are 0. For CMA instruction, your 9th bit is 1 and all other bits are 0. Okay, so if we consider the CLA instruction, so for CLA instruction, your 11th bit is 1 and rest of the bits are 0. So your 12 bit for address field will be like 1 0 0 0 0 0 0 0 and so on. So your this 4 bit will be like 8 and this 4 bit will be like 0 and the next 4 bits will be like 0. Okay, so for the CLA instruction, your operation code will be like 7 8 0 0. Similarly, if we consider a second instruction, that is CMA instruction. So for the CMA instruction, your 9th bit is 1 and rest of the bits are 0. So for this instruction, your operation code or hex code will be like 7 will be fixed for all of your resistor reference instruction. For CMA, 9th bit is 1, that means here 4 bit will be 2, then 0 and then 0. So your operation code or hex code for the CMA instruction is like 7200. Here this H represents your hex code. Okay, here this H represents your hex code. So by this way we can see how you can represent your resistor reference instruction. Next we will see the IO reference instruction. For IO reference instruction we have total 6 instructions. These are like INT, OUT, SKI, SKO, ION and IOF. For INP instruction, your input character is read from your input device and stored in the accumulator. For this OUT instruction, your character from the accumulator is stored into the output resistor. For SKI and SKO instruction, your input flag and output flags are checked. In SKI instruction, skip if your input flag is 1. If your input flag is checked and if it is 1, that will depend upon some result, and according to that your instructions branching will be decided. If this flag is 1, then your next instruction is going to be skipped. And similarly for SKO. And next to instruction ION and IOF are used for enabling or disabling interrupt. ION is for interrupt on and IOF is for interrupt off. So by this way you can use this IO reference instruction. And for this IO reference instruction, your 4 bits for operation code are fixed, and these are like 1, 1, 1, 1. And rest of the bits will depend upon your operation. And for each one of instruction, one of the bits are 1. For example, if we consider INP instructions, for INP instruction your 11th bit is 1 and rest of the bits are 0. So according to that, your operation code, or you can say hex code for this instruction, will be like F800. And similarly, if we consider a second instruction like OUT, then for OUT instruction you have 10th bit 1, so that your operation code will be like F400 and so on for all other instructions. So by this way we can use this IO reference instruction. If we summarize all of these things, then we can say that each instruction format has a 16-bit. The operation code part of the instruction contains the 3-bit, and the meaning of the remaining 13 bits depends on the operation code and counter. A memory reference instruction uses the 12 bits to specify an address and the 1 bit to specify the addressing mode I. If I is equals to 0, the direct addressing, and if I is equals to 1, then you use the indirect addressing. Okay, the resistor reference instructions are recognized by the operation code 111 with the 0 at the leftmost bit, or you can say 15th bit. And for the resistor reference instruction specifies the operation or the rest of or the test on the accumulator resistor. An operand from the memory is not needed, therefore the other 12 bits are used to specify the operation or test for the execution, as we have discussed, and depending upon that we have total 12 instructions. An input output instruction does not need the reference to the memory and is recognized by the operation code 111 with ith bit 1, or you can say 15th bit 1, and the remaining 12 bits are used to specify the type of the input or output operation or the test to be performed. So by this way we can use this input output or resistor reference or memory reference instruction. So we are ending our today's session over here. If you have any query, then you can contact me.